Welcome grade 7 and 8 to a time once again where we get to jump into science and learn a lot more about the atom. This incredibly small but incredibly awesome part of God's creation that basically creates the building block of all the stuff that's around us. Now, before we jump too far into this, I know some of you might be wondering about the periodic tables quiz that we have coming up. And don't worry, we are still having our periodic tables quiz. It's not going to be right away, though. We're going to try to have it when we're back in person. So still keep practicing those first 20 elements from the periodic table in the proper order, knowing their atomic symbol and their atomic name. But the way that things are going to work while we're online is that I'm going to be creating these science videos for you. And I'm going to be posting these videos on Tuesdays and Thursdays. I know for some of you that's your normal science class days. For others of you, that might be kind of shifted by a day. And the goal is that you are watching those videos on those days. And then on Fridays, I'm going to have a Google form. And it's just going to be a check-in to see if you remember the different things that I talked about that we went over in our videos. So you'll be required to complete that as well on Fridays, and that'll kind of finish off your week when it comes to your work for science. So we're not going to have a live stream for science, but it's going to be in this format. That way you can kind of do it whenever it works for you in the afternoons on those days. Well, we've been talking about the atom so far. And in our talk about the atom, we have learned a lot about the different history leading up to the atom. And we've learned about how they went all the way from the idea of an atom being this uncuttable particle, something that was sort of a theory of something that must sort of exist, to the fleshed out idea of what it is now. And as we continue to have more and more different scientific instruments to be able to look deeper, to be able to explore more, to be able to see the different effects of the things that are around incredibly small stuff, we're able to learn a little bit more and put more puzzle pieces into that idea of what an atom is. So today we're going to begin to unpack a little bit more about the structure of an atom, or at least start to, as we take a look at the makeup of the different things that are inside of it. So if the atom were the size of a football stadium, we have a picture of a football stadium there, let's think about if that whole thing were an atom, what would the size of the nucleus, the middle part, the part that we're going to see a little bit later on, has almost all of the mass or weight to the atom, how big would that be compared to the atom itself? Well, if you were thinking the size of the football field, you would be wrong. It's even smaller. If you were thinking it's the size of two football teams huddled together, well, it's even smaller than that. If you're thinking it's the size of just one football player, yep, even smaller yet. And in fact, the size of the nucleus of an atom would be about the size of a piece of popcorn. Incredibly small in comparison to an atom the size of a football stadium. And yet, as we're going to see, that incredibly small piece of it has an incredibly important role to play, and it's where almost the entire weight or mass of the atom comes from. Scientists have continued to learn more about the size and structure of the atom since Niels Bohr, someone who we learned about earlier in our history of the atom, made his model of what it could potentially look like. In 1926, Austrian physicist Erwin Schrödinger developed a new model. He called it the electron cloud model of the atom. And this model shows all electrons, which are the negatively charged particles surrounding the nucleus of an atom, all these electrons in what we call an electron cloud, kind of existing in spots around the nucleus. So it's not quite the way that we sometimes picture an atom where we have them flying all the way around, even though we still sometimes talk about it that way, and we still might draw it that way. It's really more like they're in this general area in this field instead. It's a region of space where a particular electron is most likely to be found. If an atom were a beehive, for example, the electron clouds would sort of be the area where the bees are most likely to be found buzzing around inside of the hive. Today's model of the atom includes a tiny nucleus in the middle with electrons in clouds around the nucleus. The negatively charged electrons in electron clouds account for most of the atom's volume or space, the space that it takes up. But the nucleus is the part of the atom that contains most of the atom's mass or weight. The nucleus is positively charged because it contains the positively charged particles called protons. So you'll see here we have, again, this is one of our older, not quite accurate models of an atom, but you'll see that the electrons are flying around the outside, and the center, the nucleus, that's where we have the positive protons and the neutral neutrons. So the protons, the nucleus is positively charged because it contains the protons, which have a positive charge inside the nucleus. The charge of a proton we would say is +1. So if we want to think of it sort of like a math question, protons are +1, electrons are -1, and then we're also going to see later on we have neutrons, which don't really have either charge. A neutral atom is one that has the same number of protons and electrons. So again, if you want to think of this like pluses and minuses, we can kind of think of it almost like a scale where we're balancing things as well. If I have 10 protons, it's like I have +10. And if I have 10 electrons, it's like I have -10. And if I put a +10 and a -10 together, I get 0. And we would say that that is neutral then. That's completely balanced. It doesn't have more pluses or protons than negatives or electrons. We're going to look at different examples later on where that balance isn't quite there, but right now we're going to say that the number of protons and the number of electrons, we want them to be the same so that it can be neutral, so that it can be balanced. The positive and negative charges then help to balance each other out. Jumping ahead a little bit, in 1932, we learned about an English scientist named James Chadwick, and James Chadwick was known for discovering the neutron. The neutron is the particles that have no charge or a neutral charge that are also found within the nucleus of the atom. So the nucleus has neutrons and protons, but nucleus don't have any charge. Protons have a positive charge, and then the electrons flying around on the outside, those are the ones that have that negative charge. Particles with the same charge, such as protons, repel each other and kind of push each other away. But what's kind of neat is that the neutrons, they form such a strong attractive force with the protons that it does keep them together in the nucleus itself. The attractive force is strong enough to overcome the protons pushing against each other, which would rip the nucleus apart. Atoms are incredibly small. We've said this a lot already too, but atoms, let's put this into perspective of what we really mean by the fact that they are small. We know that the nucleus of an atom is so incredibly small in comparison with the atom itself. But what about just one single atom? Well, it's really impossible to imagine their size on its own, let alone the size of protons, neutrons, and electrons. For example, if we just had a dot or a period at the end of a sentence, well, that could hold well over 1,000 atoms just in that. Probably even much more than that. Atoms generally range in size from 0.00000001 centimeters long to 0.00000005 centimeters long. That's incredibly small. If you were writing it in scientific notation, which is something that grade 8s I know we've practiced a little bit more of, that would be 1 times 10 to the power of -8, or 5 times 10 to the power of -8. So, size-wise, they're really small. What about weight? What about their mass? Are they pretty heavy or are they pretty light? Well, you can probably imagine, based on how small they are, they're incredibly light as well. We're actually going to take a look, first of all, at the lightest atom, which is a hydrogen atom. And a hydrogen atom, well, it would take this many hydrogen atoms, and I'm not going to even attempt to read that number. Again, if you want to figure out what that is, it's basically 1.6 times 10 to the power of 24. So if you took 1.6 and then moved the decimal 24 places over and filled in the rest with zeros, this is the number you'd get. And it would take this many hydrogen atoms to weigh or to have the same mass as a paperclip. That's incredibly small. That, just to put that into perspective, how many hydrogen atoms we would actually need just to weigh the same amount as a paperclip is crazy. A paperclip weighs roughly 1 gram. So if you wanted to take a look at the hydrogen atoms, they weigh about 1.6 times 10 to the power of negative 24 grams. Although the protons, neutrons, and electrons are extremely small, they do play a very important role in the atom and therefore in the world around us. It always blows my mind how something so incredibly and ridiculously small end up being the building blocks of the world around us. Something that we have a hard time wrapping our heads around, and yet God spoke into existence. I always find that incredible. Each kind of atom has a specific number of protons that determine the type of element that it is. Just by changing the number of protons, even just by 1, and we would have a completely different atom. An atom with 1 proton in its nucleus is always going to be a hydrogen atom. We'll take a look at this later on when we take a look at how can we tell what atom it is just by knowing the numbers of protons, neutrons, and electrons. And also, how can we take a look at an atom or an element on the periodic table, and how can we determine how many protons, neutrons, and electrons it is. But for now, anytime you see an atom that just has 1 single proton, it's a hydrogen atom. No matter what, it's a hydrogen atom. An atom with 2 protons in the nucleus is always going to be a helium atom. You might start to see a trend. One with 3 is always going to be a lithium atom. One with 4 is always going to be a beryllium atom. And so you might start to see a bit of a trend that the number of protons is really important and actually matches the atomic number on the periodic table. So you're learning about atoms 1 to 20 or elements 1 to 20 on the periodic table. So if I said, atom number 20, the atomic number 20 on the periodic table, calcium, we would be able to tell that it has 20 protons because it's atomic number 20. That number of protons in an atom is so incredibly important that that's what we use to number it on the periodic table. We're going to get back to that later on, but that's a really important concept here. The number of protons in the nucleus of the atom is what we call its atomic number. Scientists develop a unit also to express the size of the particles in atoms. It would be kind of ridiculous for us to use this big, huge, giant number to talk about how much an atom weighs. And so instead, scientists have come up with their own unit of measurement to talk about things that are so incredibly small. We can't talk about grams. Can't even talk about milligrams or anything even much smaller. And so scientists have their own unit called an atomic mass unit. And 1 atomic mass unit is about what's here. It's about 1.6 times 10 to the power of negative 24 grams. But we don't really worry about that too much. What we do care about is how can we figure out the weight or the mass of an atom using this atomic mass units? And it actually becomes kind of easy to figure out. And that's because when scientists assigned this unit, this was about the mass of 1 proton. But what's interesting is that it's also the mass of one neutron. So 1 neutron weighs 1 AMU, 1 proton weighs 1 AMU. So 1 neutron plus 1 proton is 2 AMUs, or 2 atomic mass units. But what about the electron? Well, strangely enough, the electron, we kind of have here that it weighs 0. But that doesn't really make sense. Can something really have no mass? Well, for it to be matter, it does have to have a bit of a mass, even if it's incredibly small. So it doesn't technically weigh 0 AMUs, but it is so incredibly light compared to a proton and a neutron that we don't often consider the mass of an electron when we're talking about how much an atom weighs. It would be like saying, how much does the Earth weigh? Now, how much does it weigh now if we add a feather on top of it? You'd see how it's such an incredibly small difference that we would almost say that it makes no difference at all. Technically, yes, it makes a difference. We just added the weight of a feather to the weight of the Earth. But when we're talking about the size difference and the mass difference between the two, it's not going to make much of a difference at all here. So the same sort of way, when we're talking about how much an atom weighs using atomic mass units, we don't really count the number of electrons. So what that means is that the entire mass of an electron is found in the protons and the neutrons, or another way of saying that is the entire mass of the atom is found within that nucleus. And that's going to be another important part that we're going to try to figure out. And in our next video, we're going to see how we can actually use that to be able to figure out the number of neutrons, the number of protons, and the number of electrons in any atom on the periodic table. Because the periodic table gives us the atomic number, which is the number of protons. And we know that for it to be balanced, the number of protons and the number of electrons have to be the same. And we know that it gives us the mass at the very bottom, the atomic mass, and the mass is the number of protons plus the number of neutrons. We're going to see later on how we can use that to help figure out the number of each of those in an atom. Well, so the mass number is the number of protons plus the number of neutrons. We're going to get to that and unpack that a lot more in our next video next week. Well, hopefully you learned a little bit more about the structure of an atom here. I just want to remind you to stay tuned on Friday in your Google Classroom. You will find a Google form, and that Google form will have a couple of questions based on this video here, just to kind of show me that you were understanding or paying attention to what was going on as we talked about the different parts of the structure of the atom. I'll have more videos for you next week, but otherwise, I hope you guys have a great rest of your day and a great rest of your week. Take care, grade 7 and 8.